The cables that charge phones, sync data, and keep devices running, they seem simple. But behind every strong, flexible USB cable is a fascinating process where ultra-fine copper, molten plastic, weaving machines, and precision tools come together in perfect sync. Right from the raw copper wires to the final bend test that breaks them, there's a whole world hiding inside every wire. It all begins with copper. Not just one strand, but 50 razor-thin copper threads that come together to form a single strong conductor. They're twisted or stranded into one bundle. It's not just about strength, though that matters, it's about flexibility. A single thick wire would snap with repeated bending. But twist 50 tiny threads, and you get the strength of a rope with the bendiness of a vine. This stranding process is a dance of precision, where every copper strand must flow in perfect alignment. And the machine that handles this, it doesn't pause, doesn't blink, just feeds the wires in, spins them with rhythmic consistency, and sends out perfectly stranded cores. Now, stranded wires alone aren't enough. These tiny conductors have to be shielded from the chaos of the world, electromagnetic interference, temperature shifts, friction. That's where shielding steps in. A wrap of aluminum foil comes around the stranded core, turning the cable into a mini fortress. This isn't ordinary foil either. It's ultra-thin, lightweight, but incredibly effective at bouncing off stray signals. Wi-Fi routers, Bluetooth devices, electrical noise, all of it blocked out. This shield ensures that when data flows, it flows clean and fast. Inside a typical USB cable, there are usually 4 internal wires, each one insulated, color-coded, and ready to transmit power and data. But before they can be bundled into the final cable, something clever happens. Talcum powder, yeah, baby powder, is dusted between these wires. Why? Because when the plastic sheath is extruded around them, they shouldn't stick together. Talcum keeps everything smooth, letting the wires move slightly within the sheath without damaging each other over time. This tiny step makes a massive difference. Without talcum, the plastic sheath could cling to the wires too tightly, causing stress points that wear down over time. Even a millimeter of movement can protect a cable from breaking internally. And it's not just sprinkled on randomly, it's applied with specialized dispensers that coat each wire evenly, ensuring no clumps or bare spots. It's almost invisible when applied, but its presence is crucial. This powder layer acts like a silent guardian, reducing friction, absorbing micro vibrations, and even helping during the cooling phase after extrusion. It also plays a role in how the cable handles long-term use. When the cable bends, twists, or stretches, the internal wires can glide subtly inside the sheath instead of locking up. This gliding motion is what extends the life of the cable, especially under daily stress like being coiled, pulled from pockets, or jammed behind desks. The cable remains flexible, not because the outer sheath is soft, but because the inside isn't fighting against itself. Even during testing, cables with properly applied talcum show fewer failures in the flexibility and stress tests. It's such a small addition, but it's like adding lube to an engine. The system just works better. It's another example of how the tiniest details in manufacturing are often the most important. Most users will never know it's there, but every time a cable survives another bend, another twist, another accidental yank, talcum deserves some of the credit. And then comes the extrusion. Picture a hot pressurized machine forcing molten plastic over the wire core, like squeezing toothpaste onto a brush. The sheath forms instantly, but it's soft at first, so it hits a cooling tank right after, where cold water helps it solidify into that familiar flexible outer layer. Once it's cooled, a quick check ensures the diameter is just right. Too thick, and it becomes clunky. Too thin, and it risks breaking. Consistency here means quality later. At this point, the cable's starting to look familiar, but it's still missing one of the most critical layers, the braid. Now this is the part that's honestly mesmerizing to watch. A USB data cable braiding machine comes to life like a maypole dance, spindles spinning, threads flying as nylon or polyester fibers wrap around the cable with hypnotic speed and precision. It's not just for looks. Though yes, the nylon does come in a rainbow of colors and gives cables that textured premium feel. But it's also about strength. This braided layer massively improves wear resistance. Drag it across a desk 1,000 times, stuff it into backpacks, twist it in weird angles. That nylon shell can take it. On some machines, up to 48 carriers spin at once, moving at speeds as high as 360 RPM, creating an intricate woven layer in seconds. And the best part? It's all automated. Just feed in the cable, set the bobbins, and watch the machine perform its dance. What's even cooler is that this braided shell isn't just about toughness. It adds electromagnetic shielding too, especially when woven with tin-plated copper or aluminum magnesium wire. In some cases, the shielding efficiency reaches 60 decibels at 1 gigahertz, which means it's blocking out a ton of interference. That's not something you see, but it's the reason why your cable works reliably in noisy environments. Of course, machines do a lot, but not everything. Human hands still play a role, and a crucial one. There's finesse needed in certain stages that even the most advanced robot arm can't replicate. Not yet, anyway. For example, when it's time to attach the USB connectors, people often prep the cable ends manually. The outer sheath is stripped, the wires exposed and trimmed with precision, then comes the soldering. USB Type-A, the classic rectangular connector, and USB Type-C. Flux is applied to ensure strong oxidation-free joints, and the heat must be just right. Too hot, and you'll scorch the wire. Too cool, and the solder won't bond correctly. That delicate balance is something no machine can fully feel. It takes human intuition. Some factories have semi-automated soldering stations where machines assist with the repetitive motions, but the prep work and final inspections are still handled by technicians. Technicians often check each unit by giving a firm tug after assembly, verifying the joint's integrity without needing software or sensors. So while machines speed things up and keep the process efficient, the hands-on work adds the reliability. Every cable is checked for visual flaws, uneven sheaths, misaligned connectors, discoloration, or anything that might hint at deeper issues. These aren't just cosmetic checks. A small flaw on the outside can mean a big problem inside, so this final pass ensures that every cable not only works, it looks like it should. Now, here's where things get really serious. Ever wonder how cables claim to survive thousands of bends? There's an actual robot that tests that. It bends the cable again and again in tight angles, simulating the way users twist and turn them in real life. This machine does the same movement over 10,000 times. Eventually, even the strongest cable will snap, but the goal is to find out when. That breaking point tells manufacturers whether their materials and designs are truly holding up to real-world use. The test rig looks simple at first, just a robotic arm moving rhythmically, but it's doing something vital. Each bend happens at a precise angle with measured force, replicating the common abuse a cable takes, being yanked off desks, coiled and uncoiled, twisted while charging in bed, or bent at weird angles inside backpacks. Over time, these small motions can cause internal fractures, even when the outer sheath looks perfectly fine. During this endurance test, high-speed sensors track the resistance and continuity of the cable in real time. The moment even one internal wire breaks or loses connection, the test stops. The engineers then pull that cable apart and inspect where and how it failed. Did the copper strand snap? Did the solder give out? Or did the plastic stretch and shift too much? These failures become lessons, directly influencing future designs. Some cables are tested in batches of hundreds. Results are logged, charted, and compared across materials, manufacturing variations, and even different braiding techniques. It's not just about pass or fail, it's about understanding durability in the harshest conditions. Brands that advertise higher bend counts are often those that invest heavily in this type of stress testing. What's even more interesting is how certain reinforcements, like braided nylon and flexible strain relief designs, consistently extend cable lifespan. In some premium cables, the breaking point doesn't come until after 20,000 or even 30,000 bends, nearly triple the average. Those stats aren't just marketing fluff, They're born from months of physical punishment in testing labs. And it's not just one bend axis being tested. Some setups test side-to-side motion, some test vertical strain, and others rotate the connector while bending the cable, which is a common movement when devices shift during charging. All of this helps build a realistic picture of how a cable survives in hands, pockets, and under desks. At the end of the day, these repetitive motions separate cables that just look good from those that actually perform. That little sticker saying 10,000 bend lifespan? It's backed by relentless testing, mechanical arms, and teams of engineers watching every snap and shift. It's the kind of behind-the-scenes torture that makes sure the cable you grab in a rush doesn't fail when it matters most. Cables that survive longer get rated higher. Some of the best can handle over 30,000 bends. Others start failing around 10,000. Either way, this test separates the strong from the weak and shows whether the braided nylon, the stranded copper, the soldered joints, and the injected casing all do their job as one solid unit. And in the end, it's not just about surviving, it's about delivering. Some cables, like high-performance USB-C models, offer fast-charging capabilities up to 66 watts. That's enough to power tablets, laptops, even some small appliances. And to hit that kind of power, everything has to be built to spec. From the wire gauge to the shielding to the soldering and connector type, every part matters. That's the full journey. From the raw copper strands all the way to the final bend test and performance rating, it's a mix of science, engineering, craftsmanship, and high-speed machines working in harmony. And even though a USB cable might seem small, the technology inside is anything but. So the next time one of those cables powers up a phone, syncs your files, or charges a smartwatch, that's not just a wire. It's a result of meticulous design, careful testing, and some truly mesmerizing machines spinning, soldering, and shaping the strongest wire that lives in your pocket. Like this deep dive? Go ahead, hit that subscribe button, and join the channel for more behind-the-scenes breakdowns of how the tech you use every day is built. There's always more to uncover, and you're going to want to see it.